Okay, so welcome and thanks for coming. I'm Mike Dahm, and this is the Toronto C++ user group. I had in mind, I thought maybe I'd just do a quick show of hands. How many people have been here? This is our 4th meeting. How many people have made all 4? Okay. How many have been to 3? To 2? And how many is this the first one they've been to? Wow. Okay. To me, that's almost even. I feel like it was almost equally distributed. Great. Okay. So the land on which we're meeting has been a site of human activity for 15,000 years. We recognize the enduring presence of indigenous people connected to and on this land. We're grateful for the opportunity to gather here and work in this community, and we commit ourselves to the work of reconciliation with indigenous peoples. So I want to thank our sponsors. As it has been the whole time, Autodesk is our hosting sponsor. This is their space. And they also will be contributing the pizza if it comes. It will come. The pizza will come. And Casey is not here, but Casey is instrumental in coordinating things. She's on vacation right now, but I want to especially thank Casey Conception. And also, we are a closely affiliated group of the ACCU. I think we mentioned that last time. You might see the magazines that we have on the entry table there. Take a look at them in the breaks. ACCU is an organization for anyone interested in developing and improving programming skills, and their motto is professionalism in programming. So in particular, they run some conferences, and you can go look on YouTube, and the content is absolutely fantastic, so I encourage you to do that. So other thank yous. My co-organizer, Jason Walter, is here. I always want to shout out to Include C++. I'm sure I've said it before. It's a global, inclusive, and diverse community for developers interested in C++. So one of their main activities, they have a Discord. Is anybody here not familiar with Discord? Okay, everybody knows Discord. Discord is what we used to call IRC, and now we call Slack. Anyway, this Discord is fantastic. It's quite a great community of people on there. They know a tremendous amount about C++, but most importantly, it's a tiny view into, in my opinion, what the world could be. You enter a place where everybody is automatically your friend. Everybody automatically wants to help you, and they will. So if there's one thing you take away from any of these user group meetings, is get on that Discord. Start being active, start asking questions, start answering questions, and it's going to make your life better. And I also want to thank Kate Gregory, who's not here tonight, friend of the group. The group wouldn't have happened without her, that's for sure. Okay, so upcoming events on the C++ calendar. So we just have finished the Cologne meeting of the standards group, and we have just finished CPPCon, which will give you some information on what we thought of it. Coming up, C++ Russia. Is from Halloween to November 1st. And there'll be another standards meeting in Belfast. That's going to be November 4th to the 9th. And if you recall, C++ 20 is feature complete, and now we're just doing the bug fixing. So we know that contracts got dropped last time, and I think that non-class template parameters are on the fence. Botan, can you confirm that? Okay, so there was an attempt to remove them, but they're still in. And some of that came up, I think, at CPPCon, because the problem were some edge cases relating to differences in structural equality and the behavior of the equals operator. The two are a bit confused, and so in some edge cases, there was some strange behavior. That's my understanding anyway. Anyway, I personally hope that they make it in. Okay, then ACCU will having its autumn conference, November 11th to 12th, and if you're keeping track, that is like 2 days after the committee meeting ends, and that's also going to be in Belfast, so you can double head that. November 14th to 16th, Meeting C++ is going to be having it. That is a giant C++ conference. By the way, I've looked at the itineraries today of all these conferences, and they look fantastic. So if there's any way you can get there, you should. Code Dive 2019 is in Poland, November 20 to 21st. And C++ Core Hard Conference will be in Minsk, in Belarus, November 29th to 30th. Again, I looked at all the schedules of all these. Fantastic. If you can get there, get there. I know they're a bit far. So now, I want to talk a little bit about CPPCon. Has anybody here not heard of CPPCon? Good. All right, so CPPCon just wrapped up. It was a full week. It was the first year in a new venue. It was always in Bellevue, Washington, near Seattle. And this year it was at a brand new conference center just by the airport, I would say, in basically Denver. And Sarah says it's not Denver. No, it's true. It was more like an airport than a Denver. And it's a brand new facility, so they're working out some kinks, but it is going to be there for the next 5 years, and it's a place where the conference is going to have no trouble growing. I think it's much easier to organize there, and I think that the sort of growing pains. I think the facility opened 3 months ago. So anyway, we didn't go there for the food or the pools. We went there for the content, and it was great. So on a personal note, I'll start, which is include C++, in case you haven't heard of them. There was a dinner celebrating their 2-year anniversary, and it was my honor to be on a panel at that banquet, basically discussing the impact that Include has, where we'd like it to go. And it was both spectacular for me and also terrifying. I was presenting to Chandler Carruth was in the room, Herb Sutter. I was trying not to even notice who was in the room, but I'm saying these things and trying to stay calm. But the nutshell is, what I said is I would like that group to turn inside out and become not a group within the C++ community, but become something that we just automatically associate with C++. I'd like the whole community to be inclusive that way. So anyway, nervous for me, but also really fantastic. Okay, so the obvious theme, I'm not going to talk about specific talks, I'm just going to talk about some themes. C++ 20 was a big theme. Now that we know what features are in it, we can talk about it much more. And I would say that the biggest themes were concepts and coroutines, but others may contradict me. But there was a lot of content about that. Well, okay, modules. There was definitely a lot of content related to modules. So people are talking about it. Compilers are starting to support it. People are talking about the implementation details, how the usage patterns are going to be. So a lot of the talks you'll see are going to be based around those ideas. Not surprisingly, but I have to say I was a little surprised, is that one of the central themes was performance and even some questions about performance. So the idea, so Chandler Carruth, he had a talk that stands out, basically talking about zero cost abstractions, which has been it's been a major theme in C++ recently. The idea to come up with a high-level abstraction that actually, once the compilation is done, has absolutely zero cost. So the poster child for that is always unique pointer. And he gave a talk showing that it's absolutely not true. There is a runtime cost, even to unique pointer. So that was a very interesting talk. And he's also talking about other types of costs that abstractions might have, in the broader question of costs. There's compile time costs, but then there's also human costs, all these things. So that was very interesting. A lot of it was very low level, and the harrowing and terrifying theme that I saw come up 3 times at the conference was branch prediction. So the idea was that in 3 separate cases, people were doing profiling of their software and realized that the dominant factor in the speed was missed branch prediction. One of them was Andrei Alexandrescu talking about binary search. Probably the scariest to me, because if you think about it, at a high level binary search, is kind of a quest to make every branch meaningful. But what's a meaningful branch? A meaningful branch is a branch which is 50-50. And that's not a predictable branch. So all of a sudden, this thing which is the goal of so many algorithms and the goal of a lot of our algorithmic training turns out to actually start to be a negative. And you have to start to do things that are counter to the intuition that you've learned in order to make branches predictable. So another example of that was trying to do bounding box check. And if you think about it, there's a left side and a right side to a bounding box. And there's a narrow middle. So if you test against the left side, that's a 50-50 test. If you test against the right side, that's a 50-50 test. So if you code it naively, you're left with two 50-50 tests. Each of those is an unpredictable branch, and the pipeline will stall for a very long time, and the performance will go to nothing. So what you have to do is merge the conditions sort of mathematically, logically. So you make a bool for one, make a bool for the other, and then do a single branch on the bools. So now your question you're asking the compiler to generate code for is, was it inside this narrow ribbon? Chances are very small that it's in the narrow ribbon. Now we've got a predictable branch. So if you think about how subtle that is when you're looking at the code, and hopefully you guys are better than me, I don't think in these terms when I'm writing average code. But the compiler doesn't have the ability to look at a high enough level in a lot of cases to do that merging. So I think more and more we're going to have to start to do that. So that was performance. And the other one theme that kept coming up is kind of C++ is the weight it feels of history and back compatibility, and how is that going to influence the path forward? How should C++ be responding directly to new programming languages like Rust, which don't have such baggage? How do we deal with that situation? And I think that was in highest relief. There's a proposal for C++ epochs. Has anyone heard of that proposal? Okay, yeah. So it's by Vittorio Romo, and he's taking an analogy from Rust, where Rust has additions. So when they rev the language, with the equivalent of a C++ standard version, it is almost an entirely new language. And in the code at the top, you put what addition it is, and the compiler will work on the code versus the addition that you have done. So he's proposing that. So instead of deprecating features, you just allow older code to declare that it's in an older epoch of C++. And it's opt-in for that. Now, of course, if you want one new feature, you have to take them all. Nobody is proposing to fragment the language, but it's more like making these formal waypoints. So there was a committee fireside chat where this issue was raised, and things got pretty crazy. You could start to see who was for it and who was against it. So anyway, for me, it was something interesting to think about. So that's it. There was two other of us at CPPCon. Was anybody else at CPPCon? No. Okay. Well, next year you should all go. No, for real. It's expensive, and it's in time and money. But in terms of appreciating what you do at your work, when you get back, I don't think anything can really parallel that experience. I recommend everybody try to get there at least once. Okay. So up next, Sarah or Jason? Okay, so up next, Sarah Nason. Up next, Jason Walter.
You want to just do questions at the end?
Yeah.
Hello, can you hear me? Oh, I can hear me. I guess it's okay. Hi, I'm Sarah. I'm at Autodesk. This was my first year at CPPCon, and it was actually a pretty incredible experience. I heard chuckles when Mike suggested you go, but I second that motion. I'm a relative novice to C++. I've only been writing in it for a couple of years now, and so I wasn't sure what I'd be able to get out of this experience, whether everyone would be working at far too technical a level for me, or whether I would feel like an outsider as a result of the fact that I don't have 20 years writing in this language. And that turned out to be a complete non-issue. If you want, come talk to me about my terrifying lunch where I accidentally ended up at a table with a whole bunch of C++ bigwigs, and it was paralyzingly frightening, and they were so kind to me. It was a good experience overall. I also went to the Include dinner. I thought Mike did a great job, and it was a fantastic panel. But really, the whole week was good for me. I was fortunate enough to get to take a course for a couple of days before CPPCon proper started about modern C++ API and library design. That was given by Bob Stiegel, and if you ever have the chance to take a course from him, I couldn't recommend it more. It was full of really practical applications, lots of discussion on what makes a good function, what makes a good library, basically all the way down to the language level, and I learned a lot in 16 very intense hours. I thought instead of going into themes, as Mike did, I would give you my recommendations on the talks that I enjoyed the most. Feel free to follow up with me if any of them sound intriguing and you'd like to know the name of them or the name of the person who presented them. But in no particular order, I strongly recommend Speed is Found in the Minds of People by Andrei Alexandrescu. Mike mentioned it briefly for the applications to binary search, or binary sort, but it's really more than that. This talk is incredibly entertaining. The guy is hilarious, but beyond that, it's this way of thinking laterally about problems and exploring a space in a way that seems silly or foolish at first glance, but that actually reveals very interesting results. It was the keynote on Tuesday, and it's an hour and a half, but please get some popcorn and settle in. It is worth it. Also very much liked, on a completely different note, a talk called Non-Conforming C++, What the Committee is Hiding from You, by a man whose name I'm going to mispronounce, but Myro Knept, possibly? Any talk given by a man wearing a tinfoil hat is probably good. He was protecting himself from the committee's mind control and went into a solid hour about non-conforming C++ and things you absolutely should not do with the language, most notably storing goto labels in void pointers to create your own jump table. It was great. He was entertaining. Everything about it was wonderful, if not immediately relevant to my day-to-day job. Also recommend From Functions to Lambdas, How Do C++ Callables Really Work by Walter E. Brown. He delves into the nature of callables, starting with functions and going into lambdas more specifically, at an unbelievable level of granularity that's still very easy to understand. And if you want to know how things are moved in and out of registers and how those calls are made, definitely should look it up. And lastly, she's not here, so I don't feel so weird about referencing it, but Kate Gregory's talk, Naming is Hard, Let's Do Better. A lot of the talks I went to were unbelievably technical on a language level, and hers was no less specific, but very human in its approach. It was all about naming for clarity, naming for people, naming for your future self 2 hours from now who's gonna have no idea what you were trying to express with your function name. And she really delved into that and gave some very good do's and don'ts in an immediately usable way. So definitely look her up. I think those were my major talks. Also, if you ever go to CPPCon or if you check out the YouTube channel, please look at the lightning talks. They're usually about 5 minutes long, and some of them are absurd. My favorite was a man who decided that the most elegant expression of C++ is in the fewest bytes possible. It was a code golf problem, and he was deranged. And I say that in the best possible way. And there were other lightning talks as well that were of more concrete use, but really you just don't know what you're gonna get. It's a grab bag of randomness, and all of it was good. And I'd say just overall, I saw all sorts of talks and met all sorts of people. The level of discourse was incredibly high, and I don't think I experienced anything that I thought wasted my time, which over the course of 7 days is pretty good. I think that's it for me.
So I wrote about 6 pages of notes here, which I'm not going to go through all of them. A lot of it's reiterating what Mike and Sarah had already mentioned. I felt that this is my second year at CPPCon, and I felt that this year was a lot better than last year. It's either because I know a bit more now, or the quality has gotten better. I found, like, when I went back to my notes last year, I found that I had a lot of misses on the first day in terms of talks, but this year around, like my first day of talks, like everything I liked. I did do what Sarah mentioned. I kind of ranked the talks that I liked here, so I'll cover some of those. But go back to the themes a little bit. They did seem to highlight quite a bit what was happening in C++20 now that it is kind of locked in. In particular, the ones that I was most interested was on the area of concepts. So I went to a few talks on that side. And there were also some talks that were kind of looking forward a little bit about where the future of C++ is going. So they wanted to set the stage for people that, you know, they are trying to think about the users of C++, you know, simplify things, make it easier for people to adopt it. So they did go into like some of the themes that they're doing. You know, Herb Sutter gave a talk about what they're doing on exceptions and RTTI and how they're trying to reduce the cost of those so more people are using them. So the idea was, you know, you're getting compiled or static by default, and if you want to do the higher cost version, you can opt into that. So, you know, again, highlighting the performance first, and then you know, then do, you know, the more costly things at the end. I also went to a couple talks. So I'll go in the order that I thought was interesting here. So my first one, I recently got on a kick in algorithms. So if you ever watched Connor Hoekstra's talk and then follow the breadcrumbs that he lays behind, you go back to Sean Parent's original code seasoning talk, which is very good. So when I found out Sean Parent was going to be there, I was very excited to see his talk, which was the better code relationships. And so he always has this way of kind of simplifying concepts and being able to distill them down in their core form and kind of explain them in a way that you know, allows you to go back and want to write really good code. So I really recommend his talk. I also got Bjarne's talk at the very beginning. I thought, you know, he had a very positive vibe on the future of C++. So I thought it was very good to see that forward-looking sense. And then, of course, Andre's talk as well. That was probably one of the more entertaining talks of the attendance. A few other ones that I went to that weren't mentioned already was Andrew Sutton did a talk about what they're thinking about in terms of reflections. And it was actually, you know, very entertaining just because if you know Andrew, he's kind of just laissez-faire about things. And so he goes into a bit depth in terms of what they're doing on sort of reflections and what may look like, you know, with the caveat is that it probably will change quite a bit by the time we get to C++20. And then in my day-to-day activity, I have a need for asynchronous stuff. And any of the asynchronous tools you kind of currently have in C++ are kind of clumsy in some sense. So Eric Niebler and David Holman gave a talk about how they're trying to unify all these different ways you can do asynchronous operations in C++ and come up with an abstraction that kind of makes sense and works for all of them. And then finally, because I am in graphics and I like graphics, and Matt Godboll always gives a good talk. He did a talk at, I think it was on a Thursday or Friday, about doing path tracing in 3 different ways. So he did a path tracing in object-oriented framework, in a functional style, and in a data-driven style. And he was kind of comparing, contrasting the different ways that you can write this code. And what was the most interesting thing to me is, like, if you take a certain language, and I do like to look at other languages, some languages are really good at one thing, or, you know, really good at object-oriented, really good at functional. But, you know, with C++, you kind of can mash all these different kinds together and use what you want to use. So that was kind of the main takeaway for me on that. So I also wanted to mention that this year, Arthur O'Dwyer, he did a series of talks, or he organized a series of talks called Back to Basics. And I thought that was good because last year it was kind of intimidating because there's very high technical focus on like a lot of new features and like template metaprogramming and all the stuff. But he took the approach that, well, we need to make it more, acceptable, bring in a larger audience to C++, and especially the conference. So the back to basics was kind of just reviewing sort of the core concepts of C++, the sort of the best practices that are out there right now, and reintroduce those in a unified way. So I thought that was good, although I didn't go to all those, but I did hear a lot of good feedback on that side. So that's all I had on my side.
Okay, so does anybody have any CPPCon questions for the three of us that were there? Not a single question. All right. I have a question for you. We mentioned lightning talks. Lightning talks are a series of talks where people come and give a five-minute talk. So a session will have maybe up to 20 5-minute talks, bang, 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 all different topics. Really fun atmosphere. And we learned that a lot of the user groups are doing lightning talks. So what I'm interested in knowing is how many of you would ever consider giving a lightning talk at one of our user group meetings? Okay. How many think it's a good idea for a session or part of a session? Okay. All right. That looks like it's a go. I've seen, by the way, a great lightning talk by Mark Allen, who is here, at last year's CPPCon. I'm sure he'd be happy to help you come up with good ideas. So we'll work towards that. All right, so it's 7:35, and there's still no pizza. So I would like to introduce our speaker for tonight, Greg Blair. Greg has an extensive career in high-performance computing, starting in 1975, writing weather forecast models on what was then the world's fastest supercomputer, the Cray Cyber 76. He's been working continuously in C++ since then, with some breaks just to sail to Australia and back.
6 years.
6-year break to sail to Australia and back. He taught C++ more recently at Seneca College for 5 years. He's currently the director of software at Epic Blockchain Technologies. No relation to the Epic where I work, but good name. And today he's going to give us a gentle introduction to C++ threading. Let's hear it for Greg.
Okay, I got to talk about that airplane for a tenth of a second. If you happen to Google C++ 17, whatever, and you leave out the plus, you get the C17 Loadmaster. So that's what you get if you Google C17 threads or something like that. You'll get the airplane. Okay, so much for the airplane. Okay, page down. What is a program? And this is where it all starts. So a program is typically some sort of data which consists of your data, your heap, and your stack. And typically your data is loaded, like constants and strings and things like that, are loaded at the low memory address. And at high memory address, you have a stack that grows down towards the low memory address. And just above your data would be the heap. So if the stack collides with the data, you have a problem. And if your heap grows into the stack, you have a problem. The other thing you have is code. So in order to execute that code, you have to know two things. You have to know which instruction you're going to execute, and you have to know where the stack is. When you call functions and push arguments onto the stack, that you get the correct stack. So if you happen to have multiple instruction pointers and multiple stacks on a computer, you can switch between them. And the code can access all the data between 0 and your high memory address, and your stacks are matched up with whatever instruction pointer you have. So if you have multiple instruction pointers, and it could be run sequentially, or it could be run in parallel. So if you have parallel processing capability, multiple cores on your machine, then you can run different streams. These streams are threads. So a thread is your common data, a common heap, and one stack reference per thread, and your code. And they all share a common address space. So if you have a wild thread, there's nothing stopping the wild thread from stomping on everything. There's no memory protection between a thread, although with some of the microcontrollers, you can set up memory protection for your region. So if you do have wild threads or non-well behaving threads, you can halt them. So all threads share the data in the heap, and each thread is a separate execution stream. So that implies or tells you that each is a private instruction pointer and a stack pointer. And if you switch between them, you switch the instruction pointer to the stack pointer, and the status register, you've done a context switch from one thread to another thread. Or this could be a program, or if there's more than one, if there's a collection of stack pointers and instruction pointers in their threads. If there's just one, it's just one program. So how do you start up a thread? You call a thread with an executable object. So you do what you want in your thread and call it a function or a function object, a function pointer to some function, or a lambda. And historically, I'm an old guy. My first language was ALGOL. And so I'm really happy when I can have nested functions inside another function, because it's just the way ALGOL works. I mean, why would you want to do it the Fortran way? Like C, you wouldn't want to do that, would you? Anyway, so I'm a big fan of lambdas. I love having lambdas and writing functions inside of functions, because the scope is only the duration of that function. When the function exits, that's it. It's not trashing out your global namespace or creating collisions with whatever. It's just plain gone. So the way to start up a thread is if you look in the documentation, you can figure out what the thread call returns. Or if you can't be bothered, just say auto thread ID equals standard thread and some function. And again, that can be a lambda or function pointer or whatever you got. And then when you're done, you wait for the functions, wait for the thread to finish. You say thread ID and you call join, and then it will wait until your thread finishes. If it's already finished, then join returns almost instantly. If you don't care to wait, you can cut the thread loose and let it fly. You can exit. You can do whatever you want. And the thread's just, let's say, decoupled from their program. If the thread exits, calls exit, you're still alive. And you can exit and the thread still runs. So that's what that thread I call to detach. And if you want to know, did somebody call detach? Can you join this thread? There's a thread thread ID joinable. It'll returns a Boolean. If you can join it, it will return true. And it's false if one of two things happen. Someone called detach and cut it loose. It's just running as a wild thread. Or someone called join, and then essentially it's in the process of executing. It need not be your thread. Somebody else called join. That's all we know. And did the join return? Maybe they called join and the thread's still going to run for another 3 or 4 hours. We don't know. Mutex. Mutex is very, very important. And it's a very simple concept. And I basically introduced it saying, it says, wait your turn. You have some critical resource that you want to restrict single use of that resource. And so you lock it with a mutex. And mutex stands for mutual exclusion, M-U-T-E-X, and it's by gentleman's agreement. So if you decide that you're going to create a lock for, let's say, the cout, so you're going to put a lock around cout calls, and every time you call cout, if you adhere to the gentleman's agreement, you'll lock cout, you'll call cout, and then hopefully you'll unlock it. But it's a gentleman's agreement. Someone can walk away with the lock in their pocket and block out anyone who's following the gentleman's agreement and says, I'm going to lock the screen before I write to it. But if someone locks it and doesn't unlock it, you have a problem. So the calls that you can do with Mutex, lock and unlock, as you might imagine, and then if you want to know if something is locked, you don't. If you call lock, you're going to wait. If someone else has it locked and you call lock, you wait until they release it. Then someone else gets the lock. You might get it if there's 30 threads lined up locking the same device, same Mutex. Someone calls lock and unlock, we don't know which one of the waiting 30 threads are going to retrieve it. So this is kind of a problem if you just want to know, is it locked? So you can call try lock. And there's 3 forms of try lock. You can just try and lock it and it'll return yes, no. If it returns yes, you got it. If it turns no, you didn't get it. And you can call try lock for a specified time. Or you can say try lock and then give it a time point, like try to lock it until midnight. After midnight, give up and return. Then you can figure out if the try lock until midnight worked or not. Or you can say try lock for 3 hours, and at the end of 3 hours it will return, and then you figure out if it worked or not. Okay, who here knows all about smart pointers? Nobody. Okay. Okay, now some more hands are coming up. Okay, so smart pointers are kind of cool. And they basically work that when a thread goes out of scope, you call the destructor, right? So if you have a very simple dumb and stupid class, that all it does is store the result of calling new. When that class goes out of scope, and if it calls the destructor, it can unlock or call delete on the memory that you allocated in new. That's a smart pointer in 25 words or less. You can do the same thing with mutexes. So you have this dumb and stupid class called unique lock or lock guard. And what it does, it locks the mutex and it arranges for when the destructor is called to unlock it. So that's polite. So if your process throws, it's going to unwind the stack, it's going to call the destructors, everything's cool, and your memory or your mutexes are unlocked, as you'd probably want. There's also recursive mutex, where you can have multiple locks from the same thread. And what have you. Okay. Condition variables. This is let's say number 3 of the big 3 things you need to know how to do. First thing is to create a thread. Second thing, to use mutexes to protect your critical regions. And the third thing is condition variables. And it's really cool. It says wait here until told to go. So your thread calls condition variable wait, and it just sort of sits there until someone taps it on the shoulder and says, okay, it's your turn, you can go. So the 3 waits, you can, again, you can say wait here, and it'll just wait indefinitely. And you can say wait until some fixed time, wait until midnight, or you can say wait for 3 hours, and you'll wait here. And at the end of the wait call, you can figure out how were you released? Were the conditions satisfied for the wait? Did the clock expire for either wait for 3 hours or wait till midnight? And then the 2 cool things about the condition variables is how do you notify the condition variable how do you tap someone on the shoulder and say, go, yeah, it's your turn, go. So there's 2 calls, notify 1, which as you probably surmised, if you have 30 threads waiting on one condition variable and say notify 1, the operating system says, number 14. You don't care, the operating system picks one and away it goes. Or you say, let them all go. Atomics. Atomics are basically a hardware instruction prefix that's put in front of your assembler code when you access a variable. And what it says is it disables interrupts for the duration of that instruction, and it enforces that only one copy of that operation is active at any given time. So you have all the usual arithmetic operations, add, subtract, plus, left shift, right shift, whatever you want. You have load atomic, store atomics is a specific call. If atomic flag tests and sets, if you want to test a flag, it'll replace the contents. And automatic threaded fences, which will create a block. So everybody has to stop there and wait while the fence operations go on. Futures. Oh, by the way, don't worry. If you don't understand any of this, it's okay, because I've got 30 little short examples and some, I don't know, 5 or 6 longer examples. And if you go through the shorter ones, it's going to make everything I'm gibbering on about right now come home. It should work. So futures, how do you get the return value from a thread? If you call a thread, it's a void return type, or the function you pass through a thread is void. So what do you do if it's not void? Well, there's 2 ways of doing that. What do you do if you have a void function that has to return a variable? Well, stick it in the argument list and pass the address of something and have it set the return value as that variable. So you can certainly do the same thing with threads. So type T, some return variable type, and thread, the function f, that's your thread function, and then you say reference ret. So reference creates a reference to it. And what are references? What's the difference between a reference and a pointer? Anyone? I'm sorry, can't hear you. I'll buy that. Now, the references are pointers. Don't believe me? Here's how you can prove it to yourself. Write a function and pass a pointer to the function. Write a function and use a reference to the variable. Dump the assembler out. It will be identical. QED. I mean, anyone? I have an example. I didn't bring it in tonight's talk, but if you want to, I can call it up and show you the assembler. I'm not making it up. It's really true. A reference is a pointer. That's how the machine executes. Okay. So method 2 of how to return a thread value is you use something called a future, and you make a function called an async, and then you get a function called get on the future. So the future is a templated instance of something. So here we have future t in pointy brackets. So you're creating an instance of a class called future that has a template parameter t, whatever it is, int, float, who cares. And you create an instance of that name and you give it a name. So I could say FUT for future. And then you assign that value, that future, to be the result of calling something called async. And that is some function. So that returns that async will return a future, assuming the function returns type t. And then to get the value when it's finished executing, just call future.get. And it'll return the value. So again, we got 2 ways of returning the values from a thread. Number 1, you use a pointer. You can actually code it as a pointer variable and with ampersand for the call and all that stuff, or you can use reference. The C++11 or C++ way is more to use references and pointers. It's all this, again, dump the assembler out. You can rest assured it's the same. Number 2 is you use the 3 calls, future, async, and get to return the function variable, the value returned by the thread. Question? So the question is, does it stall or wait? And the answer is absolutely. When you call get, it will call join and then, okay, here's what happens under the hood. You create a future of type T. So what that's going to do is going to create a memory block for a class instance that knows to call your function, and it has space in there to hold a return variable. So what it's going to do, it's going to create a new function that's going to run on the thread that has a parameter that points to that memory region. So and that function then calls your functions. Your function returns whatever it returns. The function that called it knows to store it in this squirreled away in this location. And then when you call get, it retrieves the value from that location. It's really, really simple. Oh, everybody has to swear that threads are really, really hard. Because if you tell people it's simple, you can't charge the big bucks as a consultant. And that's really, really important for me. Anyway, I know, for you guys too. So here's an example calling a future. Future double FUT equals async launch, async, comma, square root, comma, 2 dot. Okay, what's 2 dot? What type of data is 2 dot? 2 decimal point. Well, which is it? It's a double. If it would be 2 dot F would be a float, right? Okay, I just want to, it's kind of, I do want to be pedantic about that because our future says it's returning a double. And we're calling square root, which returns a double, not a float. Square root F on some C libraries would return as a floating point square root. Just call square root, you get double. So if you say future double FUT equals async launch, async, comma, square root, comma 2, that will run the square root function as a thread on that, pass it the argument of 2, so it's going to calculate the square root of 2, return it, store it in that location. When you call get, it's going to retrieve the value that you've squirreled away when the function returned. Any question about that? Okay, it's not hard, but please tell everybody it is. So again, that's what I just said, I guess. Promises, illustrate by example. So promise basically says that in the future, someone's going to return a future. So here we have a function, lambda, promise, int star. So you can see that promise is a template type, or it takes a template parameter, in this case an integer, and we're passing the address of the promise. And then when you inside the function, you're going to say p set value, let's say 42. So that sets the return value for a future to be 42. So let's run the puppy. So that we start up standard thread t, and then we say standard promise int p, and then we say future int FUT equals p dot get future. Okay? Don't worry, we'll have examples. So then to run this puppy, t equals standard thread, and then you pass it the address of the pointer, because we said in the first line there, auto function standard promise in star p. So star p, we have to say ampersand p, future.get and join. Now in this case, it doesn't call join. It will wait until the promise, or the function with the promise calls set value. So this is kind of cool. You can get an intermediary value that's calculated prior to the thread exiting. So you can have the thread calculated away, and you want to know, well, let me know when you're 50% done. So you create a promise in the future, and it says, it sets a Boolean thing, yeah, but I'm 50% there, or whatever you want. So while the thread's running, you can sort of peek at it with a promise and access or pick up values that have been set by the thread. Oh, package tasks. I don't even know if I want to talk about package tasks, but it's all part of the same thing here. And so it builds on top of promises and futures. And a package task wraps a function that returns a variable into a future, and that's about it. I mean, it's kind of a cool thing because a package task has a reset function. And when you call the reset, it resets all the promises in the future and everything like that. So what that means is that you can relaunch the thing without relaunching the task. So you can have some sort of pipeline that calculates something and feeds that variable back to the caller. Oh, spin locks. Giving up the CPU by making an operating system call can be a bad idea. Anybody know why? What happens when you make a system call and the system call completes? It jumps to the scheduler in the operating system, and the scheduler calculates for every process on the machine, the priority, sorts the priority from high to low or whatever, and as part of calculating that priority, there's a flag that says whether it's ready to run. If it's ready to run and you're the highest priority, guess what? You're the person that gets the CPU and everybody else waits. So this can be great if you're doing a lot of I/O and everything on the computer is I/O bound and you got to do it. You got to do it. But if you're doing something computationally intensive, and you don't want to give up the CPU because you don't know when you're going to get it back, giving up the CPU is a bad idea. You want to hold it as long as you can. So if you only want to lock something for a short period of time, if you call Mutex, it's going to make an operating system call, jump to the scheduler, calculate priorities, sort from high to low, look who's ready to run, and activate the process at the highest priority that's ready to run. And then you're going to make another call right away. So you can sit there spinning in the operating system, and you're created everything on, like your whole CPU is just servicing the operating system request, it's not doing any useful work for you. So if you only need to spin for a short period of time, then if you just spin on a variable, well, set something equal to zeros, while it's equal to zero, spin. As soon as it's non-zero, away you go. Also, it's a good idea to put a break in after so many loops, so you don't sit there and spin lock for hours and hours and hours. You spin lock for a second. If something didn't satisfy in a second, you have the call then. Well, what are we going to do? Maybe at this point you might back off to an operating system call. That way you're polite. You let the operating system manage when this resource is okay. And then you don't have to, you're not burning CPU cycles spinning needlessly if something's not ready. So there's a gotcha here. You got to ensure that the setter will be able to set the spin variable so the spinner can exit the infinite loop. So if the spinner's sitting there looking for a variable, and you happen to just have one core on your machine, and let's say it happens to be an embedded controller, and there's no operating system, you're just sitting there spinning with your spin lock, waiting for the other side of the spin lock to set that, is never going to get the chance because you monopolize the CPU. You're in your tight loop, and the other fellow who's going to satisfy the spin lock condition never receives any clock cycles, and you sit there and spin forever. So if you're using spin locks, you just got to be careful about that. Semaphores. Semaphores are not part of C++ 11, but they're used all over the place. And what it is a counter the max number of active threads in a critical region. So let's say you set a semaphore equal to 4, and then a thread comes along and bumps the semaphore count, and it's less than 4, so that thread continues to execute. Second guy comes along, bumps the active count threads, now 2, it's less than 4, he executes, et cetera, et cetera. 4 comes along, he bumps it, or you got four flying, and the next thread comes along, bumps it, it's greater than 4. So he will block until the variable is decremented. So when a thread exits, you decrement the count, and everybody's happy. So the guy who's waiting for it to decrement, he then executes. And you implement this with condition variables. Pipelines, barriers, sync point for multiple threads. And typically a pipeline, you have let's call them task 1 through whatever, or thread 1 through whatever. So thread 1 creates something, passes it to thread 2, passes it to thread 3, et cetera, et cetera, et cetera. So what you want is you want all the threads to come up to the top. This guy feeds the second guy feeds the third. And you want them all to start at the top. Typically with the image processing or video processing, you want to do that if you have video servers or whatever. And I'm thinking when I did the digital projector for IMAX, and we had a motion server that had all the video on it, and we had to run it through 2 warp engines, and so we had a threaded pipeline. And so you read the frame off the video server, and it's all encrypted. So it's all decrypted by the video server. It comes in, and then you have to pass it to a GPU. So you got two threads, one driving each GPU on the machine, and then you have to spark up the GPU kernel on each GPU to actually do the warp. Then you got to pull it back to the host memory, and then you got to take it out to HDSDI port out to the projectors. So again, pipeline, and as long as your frame rate, that 24 frames a second, that's 42 milliseconds in easy numbers per frame. So you got 42 milliseconds for each stage of the pipeline. Yes, your processing can take longer than 42, and you break it into threads in your pipeline. As long as each thread in your pipeline executes in less than 42, everything's cool. And don't try and execute 41.9. You want some headroom. You want some slack. So the basic thing of a pipeline is all the threads meet at a meetup point, and when the last thread arrives, you issue a notify all to everybody, then everybody flies. So you have 4 or 5 threads in your pipeline, they're all waiting, the last guy joins, and then everybody flies, and they all start executing, they come back up to the top, they all wait again. When the last guy joins, everybody flies. So that keeps your processes in sync. Thread pools. Threads take time to start up, and so the idea behind a thread pool is you start your threads up and then you reuse them. So a thread will block or wait on a condition variable looking for work. And when you place a job into a thread-safe job queue, after each job is inserted into the queue, you call notify one. You don't care which thread in a thread pool comes alive and starts to process that job. So it takes a job off the job queue and starts executing it. Similarly, you now add a second job, the second thread in the thread pool takes it and runs with it. Sooner or later, your thread pool is full. You have 27 threads, for example, in your thread pool. So thread 28, okay, it comes along. 1 through 27 are working, they're busy. And thread 28 then places the job in the job queue and goes away. So when a job finishes, it checks the job queue. Is there anything to do? If there's something to do and the job queue is not empty, take the job off the job queue and start executing it. And otherwise, you wait. You wait for something to appear in the job queue. Producer-consumer queues. They're used all over the place. And some of the stuff in computer science we all know is jargon. You got to understand the jargon or you have no clue what the people are talking about. So they typically call these things PCs, talk about PX, CY, the little X, the little Y. Can you see that up there? Little X, little Y. P1, C1, P1, CN, etc. So X is the count of producers, and Y is a count of consumers. And these producer-consumer architecture are always application dependent. There's no two alike, else you're doing the same thing. And often you use circular queues on the buffers, and sometimes you can get away with lock-free queues, meaning if the producer and consumer never can exhaust or fill up the queues, the buffer queues, then you're good to go. You do not need to lock because you don't have to worry about it. The producer will take longer than the consumer. So if the consumer is fast and can do the work quickly, you never have to wait for it. The producer never has to wait because the consumer will always be emptying it faster than the producer can fill it. Well, if that's not the case, then you have to have some sort of locking mechanism. What happens when the queue is full? The producer can't put anything more into it because it's full, so the producer has to wait. If the consumer comes along, what happens if there's nothing in it? The consumer has to wait until the producer puts something in it. So again, these are the reasons that there's no two producer-consumer queues that are identical because everything is application specific. So you talk about starring or filling, and if you're starved the queue, then There's nothing for the consumer to do, it's starved. If the queue is full, then the producer has to wait. And it gets very interesting when you go across different buses. So if you're writing to a GPU and you want to synchronize a producer-consumer queue so the producer's on the host on your CPU and your consumer is on the GPU, then you can have some very interesting anomalies going on as you push things across a PCIe bus. And that's all I wanted to do for the slides. Now we got our 30 little examples and our bigger ones. So any questions or? Go ahead.
With reference to spin-offs, description of spin-offs. So in reference to your comments on spin-locks, spin-locks, yeah, sorry for the accent. Spin-locks have, or can have a significant impact on UX and on power consumption and things like that. And modern OSs, actually, if there's no contention, they wouldn't go to kernel mode. They wouldn't do the switch. Linux or modern Windows, they have user mode mutexes. So really, you probably don't want to be using spin-locks in user mode code.
Like I said, if you're only spin locking for a few clock cycles, who cares? But if you're going to develop any sort of length of time in that spin lock, you want to look at other ways of doing it. I mean, it's everything's specific on what you're doing, and sometimes it's a good idea, and sometimes it's a really bad idea. Sometimes mutexes are a good idea. Sometimes mutexes are a really bad idea. Question?
So I was wondering if a thread is terminated before it finishes what it's doing, and then you call like that get method. What does it return in that case?
So you mean like the thread aborts?
Yeah.
Okay. So if you just call join, it will. There's no clue that the thread aborted. If you call future, you can find out the exit code of the thread and find out if it did abort.
I had a question about unique lock and lock guard. They seem
Okay.
to do substantially the same thing. So is there a reason to choose one over the other?
We have an example on that, but the answer to your question is yes.
I'll wait for the example.
Okay. A lock guard you can only call once. A unique lock you can call more than once. So you can create, look at our example.
Does unique lock have a higher cost?
I don't know. So here's all our programs. And is the pizza here? Oh, pizza's here. Okay. We should eat. Start and eat a consumption thread.
Okay, guys, let's grab some pizza, maybe bring it back to the seat. No rush, but I want to hear the rest of Greg's talk. Okay, guys. Hopefully by now everybody's had time to have some pizza. Feel free to bring it back to your chair. But I would encourage you to grab some, and let's let Greg have his say.
I know how to fix. That better? Okay, so what this example does, it shows you how to start, join, detach, and get a native handle if you want to do something with your native operating system. So what we do here, line 11, standard thread, and what's this square bracket stuff? It's a lambda. What's a lambda? A Greek alphabet letter, right? Well, C++, if you, I don't know why, but they call like inline functions that you write as one line, they call them lambdas. I don't know. But why did they call them lambdas? It was a transcription error. From what? A hat over a letter. They wrote it out as a lambda next to... Oh, okay. So it's not Greek. Okay. As a mathematician, I see Greek letters all the time. I figure it's because the Greeks invented mathematics. I don't know. But anyway, so what this is, the square bracket says it's a lambda. And if you put stuff in the square brackets, they call that the capture. It's out of the scope of tonight's talk, but if you don't understand it, you need to understand it. So basically, this says we're just accessing stuff that's inside the function. So then between the curly brackets, right here, there's the first curly. Right there's a second curly. That's the function. And then here, you notice this is a function inline thing, and there's the brackets for the thread call. So it's thread, we're passing it a function. It happens to be an inline function. And then what do I do here? We say thread. Now, this returns a thread ID. And we say, is it joinable? And if that says the thread is, so if it's joinable, it just prints nothing. Thread is nothing, joinable. And if it's not joinable, this thing returns false, and then we print the word not joinable. Then we call join, and then we should see a difference. And then we do another thread. Thread ID 2 is thread low from thread 2. Very similar to our function for the only difference is 1 and 2. And we say thread 2 is joinable, not joinable, detach. Okay? So detach, it's wild, wild west. You just let the puppy run, and you don't care what it does, and you don't care when it finishes, and you're just going to let it rip. So now we're going to say thread 2 is joinable or not joinable. We make a third thread, thread 3, and then this, what's this lambda function do? Nothing. That's right, not much. Okay. So we start printing out a few things that we can get out of the C++ 11 library. All this stuff came from 11. So we get the thread ID and the native handle. And as you'll see, it actually turns out that in this case, in this implementation, it's the same, prints the same thing. And then line 36, what's that? That's an operating system call. That's got nothing to do with C++. What's it do? It's really rude. It's the rudest thing you can do. And it says kill, and sig kill is the non-interruptibles -9. You know, that's it. When you issue sig kill, if you've got permissions to kill that puppy, it's gone. And then which puppy are you going to kill? Well, native handle is you want to call the native thread that's running under the C++ 11 thread. So the native handle return the native P thread in this case, handle. And then to that handle, we just give a P thread call or a thread call to that handle of kill, sig kill. And then we call join and exit success. And if it threw, then we print our message out. So let's just run this. So with thread 1, it starts out being joinable, say that it runs, and it's then we call join, and it says thread's not joinable. And then we thread 2, we say hello from thread 2, we detach it, it's not joinable. Then we print out the get ID and native handle, and we kill thread 3 with the kill call. So notice that the native handle and the get ID are identical. So with this implementation, now again, if I upgrade my C compiler and then it's going to update its libraries, who knows what it's going to be next week. So do not assume that get ID and native handle are the same. They're not. If you want the native handle, get the native handle. If you don't care, call get ID. Any questions on this one? Okay. So what's this one do? Well, it's very similar to the last one, only it's just a little short thing. And if I run it, so what happened? Terminate called without an active exception. How did that happen? What's going on here? Okay, line 8, I start a thread up. I print out whether it's joinable or not, and then the main function main exits. You never actually ran the thread. No, the thread ran. Thread ran. Okay. But it says terminate call without an active exception. That's a SIG alarm message. Okay. When you start a thread up, you either can let it go by calling detach and saying disconnect it from my process. I don't care what it does. Or you can join it. And if you don't join it, you get that message. So that's really, really important. That's a SIG alarm, or sorry, SIG abort call. You can trap it with the signal mechanism. You can trap all that stuff and say, oh, somebody, whatever. You can do post-processing and figure out what's going on. But it's really, really important to either detach a thread and let it run and it'll die whenever it dies, or call join and wait for it to exit. If you don't exit, you get that message. Okay. Okay, how do you pass arguments to a thread? When you create the thread, you pass the argument. So here's the thread call, right there. Then you give it some function, comma, the argument. Okay? No, it's not rocket science, but tell everybody this is really hard, okay? So here's our function between where all the carets are, and there's the argument right there, I. So for I equals 0, I less than n, I plus plus, push back. So that's a vector somewhere. Yeah, here we go, thread IDs. And then when we're done, we call join. Okay, so how many did I create? 100. So if I just run this, T3. Okay, so there they all ran. And they appear to have run sequentially. Hello from Fred Zero. They look to be sequential, but something's going on here. What's that all about? Question or answer?
So the threads all share the program's standard output, but they don't synchronize access to it. So you can get things like mixed partial outputs.
That's exactly correct. We have 100 threads. This machine, this laptop's a bit of a beast. It's got 16 cores. I really like it. If you used to do a lot of thread programming, you'll like it. It's a year and a half old. I could buy one now with more cores, but what the heck, this meets my needs. Okay. So here we're creating a little bit more scrambling. So what happens every time you call C out, that's an operating system call. So this says hello from thread I \n. So that's 1, 2, 3, 4, 5 operating system calls per thread. So if we run this, I expect to see more scrambling. I don't. Okay. Don't worry, we can get scrambling. Okay, let's explicitly give the CPU away. So, where's function nap? The standard is set sleep for 100 microseconds. So we're going to print hello, nap, we're going to give the CPU away. We're going to print from, nap, give the CPU away. Thread, nap, give the CPU away. I, nap, give the CPU away. \n, nap, give the CPU away. So we can just see here it's a little scrambled, so if I go out and print it from the... As expected. You expect to see it scrambled. If it was all nice and neat, then you know it would indicate to me that the threads are not threading. That you're looking at sequential execution. If this printed really nice, and I didn't get scrambled out, but I'm in some sort of sequential execution mode for some reason. I'll have to figure that out and figure out what's going on. So, we're creating a bunch of threads, 100 threads. And again, we're pushing a function on here. I got a function called spin. And what it's going to do, it spins on, while the start-stop duration is less than 100 microseconds. So this is similar to the nap function as before, but our nap function was very polite. It made an operating system call to say, I want to sleep for 100 microseconds. What we're going to do here, we're going to spin for 100 microseconds. So we're actually consuming CPU cycles instead of napping politely. And the rest of it's all the same. So instead of doing the nap, I call spin. And let's see what happens when I run this. Again, we get mumble jumble. Okay. Is this a duplicate of the last one? Oh, okay, and I know what's going on here. Okay. String, hello from thread, plus standard two-string I plus \n. What is that thing? What am I outing? I'm outing a string, right? Okay. Am I making an operating system call when I do it? Only the one call, the cout. So using string, if you're just printing, is a poor man's way of having your print occur all at once. It's not going to be interrupted. That string will complete when you make the operating system call. So I expect this one to be, when it runs, to be well behaved. And it certainly is. Now, was the order scrambled? Hopefully the order was scrambled. Okay, I should have brought my crappy laptop. This one's too fast, so, okay. Okay, so we saw that if you make all operating system calls, you can lose the CPU, and if you're printing something, you can get mumble-jumbled, scrambled output. So the other way of locking things, or the way to lock things, is use a mutex. So here we got mlock and munlock, line 21 and 22. So here I'm making operating system calls, hello from thread, that's one operating system call, print the number, second operating system call, \n, that's the third operating system call. But I'm locking the screen while I do that. So now when I run this thing, again, we get well-behaved output, and if we're lucky, it goes out of sequence. But it looks amazingly in sequence. Again, I should have brought my lousy laptop. But, okay, 9. Oh, okay. Again, we talked about smart pointers, where when the structure's called, the smart pointer does something, and for pointers, it calls delete, which deletes your pointer address. So if you throw or anything bad happens in your program, you deallocate all your memory that you allocated with new and pass to a smart pointer. Of course, if you call new on your own and don't pass it to a smart pointer, memory leak. So here we can do the same thing with a smart mutex. And they call it, just like you have a unique pointer for a smart pointer and shared pointer, here you have a unique lock for a mutex. And again, if we call the whole thing, it's as expected, it's going to work. And again, it works. Any questions about the unique lock? So again, here's the last one was unique lock, and this is using lock guard. So the difference is lock guard cannot be reused. This doesn't reuse it, but we'll have examples later on where we reuse it. So lock guard and unique lock essentially do the same thing. Lock guard is a little less code to execute. So if you have a choice, probably your preference is lock guard. If you need unique lock, by all means, use unique lock. If lock guard won't do the job. So again, as this thing runs, does everybody see the auto join at line 24 and 25 using a range base 4? Okay, that's a lazy way of doing it. I prefer to do range base 4. It's just so much easier. I don't have to pass into the for loop the number of threads. Who cares? It's just, but the cost of doing that is I have to create it in a vector or something like that I can then use the range base 4 down here. So I'm lazy down here, and I have to do a little bit of work up there so I can be lazy here. But to me, it's being a lazy dude that 24, 25 makes up for the pain of having to drag vector into the program. And again, it runs as expected. Okay, I mentioned tri-lock, and the 3 forms of tri-lock, remember what they were? You can tri-lock until a fixed point in time, like try until midnight, or you can say try for 3 hours or whatever, or you can just say try. So what's this program do? If tri-lock, if we get the lock, what do? What happens if we get the lock? Line 23, what do? We sleep. We hold in the lock and we're going to sleep. And then we print, okay, let's look at line 28. So if the lock is busy, if we didn't get it because someone else has it, what do? We just bump a variable called count, and we keep track of the number of times that we tried and didn't get it. And then when we do get it, we print that count out. So in line 24 right there, we print out count, set it equal to 0, bump it if we didn't get it. So you can see, because of our quarter, or whatever it is, 250, was it milliseconds or microseconds? Anyway, you can see that our thread counts are going up. Now notice the order. There's thread 3 popping up, 17, 4. And that's been scheduled for an awful long time because we just ran thread 88. There's 9. You can see the order is not going as it was in the earlier examples. Because we're now actually doing some work. I mean, we're sitting there, we're spinning, we're bumping count, and we're hogging the lock for whatever it was, a quarter second, 250 milliseconds, right? Okay? So this, to me, is starting to become more interesting. We're starting to see some stuff going on here. Okay. Thread args, call by reference, call by value. Where's my call by value? That's call by reference, that's call by reference. Oh, I must have broke it. I'm not going to belabor it because I want to go through I'll just run it. Maybe it'll be obvious. Oh, I know what this one is. Okay. So let's see what happened here. The first time we ran 1 through 10, it printed the numbers 1 through 10. The second time we ran, it printed 10 each time. Okay, so let's go take a look at that. So how did that happen? So when this runs here, this passes the address of I, and I is the thread is executing rather quickly. But if we look here, we're sleeping for a second, and we're passing the address, the reference of I. So after we slept for a second, what's the value of I? N, right? Because it's rattled through the for loop, we're passing the address of I. I's now 10. By the time that they wake up after sleeping for a second, I's 10, and all threads print out I equals 10. Okay? Make sense? Any questions? Run it again. Okay. Wrong one. Okay, deadlock. Let's say you have 2 mutexes, 2 locks. I have 2 threads. Thread 1 locks mutex 1. Thread 2 locks mutex 2. Thread 1 now wants mutex 2, but thread 2 has already locked it. Is this going to work? Is it going to work? Anybody? What's going to happen when I run this? Thread is going to print thread 1 lock mutex 1, thread 1 sleeping. Thread 1 woke up and wants to lock mutex 2, and it tries to lock it. But it's already locked by the other thread. You can see down here thread 2. It says thread 2 lock mutex 2, thread 2 sleeping. Thread 2 woke up and wants to lock mutex 1, and it's never going to complete. Is that long enough to wait? Okay. Control C. Okay. So that's deadlock. And the rule for deadlock is if you cannot grab every resource you need, you must release all your locks and go back and try again. You can also think of this as 2 one-lane bridges on a highway. So you got 2 lanes coming in, there's a 1-lane bridge, 2 lanes coming in the 1-lane bridge. So once somebody enters the first bridge and the second bridge, someone's going to have to actually back up before the second car can proceed. That's all it is, just 2 one-lane bridges. Or 27 one-lane bridges if you have 27 mutexes. And you grab 26, life was looking good, but you couldn't grab number 27. Guess what? You got to deallocate or release all the ones you've already grabbed and come back a second time and try and grab all 27. If you get it, great, do your thing. And please don't forget to release your 27 mutexes. And, okay? So the British people refer to deadlock as deadly embrace. I don't know why. I just think it's a 2 one-lane bridge problem, anyway. Now, main is a thread, right? So the fact is the previous example was between thread 1 and thread 2. There's absolutely no reason why we can't have thread 2 main. So here's our old thread 1, exactly as it was. And here's our old thread 2, now executing as part of main. And of course, you're going to get these identical results, right? It's going to hang forever until I type Control C. Race conditions. So what this one is 2 threads accessing the same variable. And they call it a race, but really it's the loser. Whoever loses the race wins. Whoever writes, okay, you both grab the same value, and you do something to it, and whoever goes last is going to be the value that's in that variable. So in this case, thread 1 picks up the variable var and bumps it. And thread 2 picks up the variable var and bumps it. This one sleeps for 500. They both sleep for 500 milliseconds. And they're going to replace the variable. So what would be nice, though, is if one thread bumps the value, the other thread took advantage of that, right? That's probably what you want. But you just have to be aware of this. And they call this, again, a race condition. To me, I understand they're saying it's a race. It's whoever goes last, though, in the race. Okay, with a race, whoever crosses the finish line first wins, right? This is the opposite. Whoever comes across last wins. It's his variable, or his value that's going to be stored in the variable. So again, if we run this thing, that was 15. And the variable is 1 at the end of the thing. Okay. This is my favorite part of threading. Threading a for loop. The reason it's my favorite part of threading is I was brought in as a consultant to fix a stinky threading problem. They spent over $1 million with a team of 5 to 8 people, depending on the month, working on this project for a year and a half, and it wasn't working. In 20 minutes, I made it work and picked up $180,000. So, which might sound like a lot of money until you look at the money they threw away and failed. So, now how did that actually work? They hired me for $120 and kept me around for a year and a half. And after a year and a half, I had enough of their coffee and they had enough of my bad jokes. So anyway, but still, threading a for loop is absolutely critical to understanding threading. If out of tonight you go away, you understand thread join, you understand there's something called mutexes, there's something called condition variables, and you know how to thread a for loop, I'm a real happy guy. You got it. You can sort out mutexes and you can sort out condition variables. You've been exposed to it. You will have seen some of it, and you'll have a good idea on how they work and what to do. But if you know how to thread a for loop, it's really a thing in demand. So let's take a look at what we got here. So constant n is $1 million plus 1, int n. And now we say a, or int I equals 0, I less than ni plus plus, ai equals 1,000 times sine pi divided by pi I divided by 180. So I is in degrees, convert it to radians, call sine. Now there's a bunch of ways of threading a for loop. Pragma OMP, OpenMP, it's been around since the mid-2000s. You've been able to do it for a very long time, and it's very simple. You just put Pragma OMP parallel 4 in front of the for loop, and some compilers know how to convert that, how to convert the for loop to run in parallel. Okay, so this is your given problem. You want to thread that for loop. And here's the lazy man way. You just put OMP parallel 4 in front of the for loop and see what happens. If it speeds it up by a factor of 2, that's, you know. Here's the real way of doing it. Figure out how many cores you have on the machine. So this thread hardware concurrency returns the number of cores that's available. And as you've been running these other programs, you've seen it prints out that there's 16 cores on the machine. Let's try and find a print statement. Yeah, there you go, there's one. There are blah, blah, blah. Okay, 16 cores on the machine. Okay. So the cores on this machine will be 16. So int n, standard thread, the number of cores, we're going to start up that many threads, 16 threads, okay? Now each thread's going to work on a chunk. And I say if n is large, we just divide by the number of cores. And we say n comma chunk, print it out, and say n is large. Now here's our threading here. Int t equals 0 for thread, t less than cores, the number of threads we're going to run. Start is t times chunk. Stop is start plus chunk. Okay, so that's going to figure out the range of variables that you want each thread to do. Now we take a look at the very last thread. The very last thread is, we're going to set it equal to the variable n. So in this case, n is 1 million plus 1. 16 does not divide evenly into 1 million plus 1. So in this case, what we need to do is ensure that the last thread is, the end case is actually thing. So you want to not just 1 million divided by 16, you want to actually do 1 million plus 1. So that ensures that you do the right number. We print these out, and it's going to calculate it and join. Now, here, if n is large, who cares? 1 million plus 1 divided by 16 gives you a number. If the number of cores, the size of the problem is small. You'll see this, let's say the n is 7 and you only have 4 cores. If you just divide by 4, then you get each thread, 1, 2, 3, each doing 1. And the last thread, 0 to 3, whatever, the last thread will then do 4. 4 plus 3 is 7. So that's not fair. So essentially, something that ran in time proportional to 7 is now going to run in time proportional to 1. Whereas if you round up the chunk size, then what happens is the threads, they go 2, 2, 2, and 1. So that's going to run in 2/7 the time that the original code ran in. If you thread just by divided by n, it's going to be 4/7. Not a big speed up when you can for free get 2/7 speed up. Anyway, I'll run this. So what this did, it did with the large number, and then it did the small with no rounding and the small with rounding. And if you take a look right here, you'll see the first 15 cores got off easy. They only had to do 1, and the last core had to do 16. Not very good, but if n's big, who cares? So look, there's the n big stuff. So you can see with n big, they're all doing 62,500, and the last one did 62,501. Who cares? So if n's big, who cares? Just divide by n, or round up if you want. It doesn't matter. But if n is small, rounding up is really, really important. Any questions? This is just timing the for loops of how much time it takes to do, and with we didn't really hit the CPU hard enough, because here's the one with the 16 cores. You can see the time. I need something more computationally intensive to really show that it's 16 times the time of these ones here. So it ran 16 cases in 18 microseconds, and it ran 1 case in 17. So most of it was set up. Similarly here, these cases here, the last one ran marginally faster than the other ones they ran in whatever. Okay. So here we do a for loop, a do-it-yourself for loop, and then an OMP parallel for, and homemade threading. I'm just going to run this. I think the 18. So this uses for each, and there was a C++ 17 with the parallel for. And notice the times. So what happened here? Why did it slow down? Like the best we did with just an ordinary for loop was 4 microseconds. And then it ran with parallel for in 11 microseconds and 7 microseconds. Here's another one here. That's a lot bigger than 4, right? What's going on? Overhead, starting the threads up. So again, threading is not free. It's great if you can start them up and do some real work. If you have something to keep the CPUs busy, go ahead. Suffer the startup overhead and put them to work. This is interesting. What this does is it's going to print a number. Each thread is going to just print 0, 1, 2, or 3, and it's going to do it 1,000 times. So in parallel, we got 4 threads, 0 through 3, and it's going to print, each one's going to print its number 1,000 times. What did you see? Is that nice uniform distribution? No. We have a bunch of zeros, a bunch of ones, a bunch of zeros, a 1, a 2, a 3, et cetera, et cetera, et cetera. A bunch more 2s, a bunch of 1s. Look down the bottom here. We have a bunch of 1s, a whole bunch of 1s, et cetera, et cetera. So thread 1, 0, 1, 2, 3, thread 1 didn't get many clock cycles until the end, when the other ones finished, and then it came along and did all its work. Thread starvation, not very good. Okay, so that's all I wanted to say about those ones. So how long does it take to start up a thread? Well, I'm just going to run this because I want to get through all my 40 examples or whatever. Okay, so there's your start-stop time. It's not free to start a thread up, and even to wait for a thread is not free. Okay? Thread return values, not going to bother with that. Or that. This one's kind of neat, I think. This prints, okay, if you return a variable, how long does it take to set that variable? So method 1 is just using a pointer, mutex, and a condition variable. So main will call the condition variable. The thread will wait until main says notify 1. And the second method is to use a future and a promise, as we talked about. And you can see the times to retrieve the value once set. So 13 microseconds and 8 microseconds, 18 microseconds, and 7 microseconds. Let's run it again and see if those numbers are significant. Okay, they kind of burble around, right? But again, so even fetching the results out of a thread take time. The synchronization point, however you do it, condition variable, mutex, future promise, they all take time. You just got to be aware of this. That's what's going on. I won't bother with package tasks. Okay. A one-shot producer-consumer queue. So we got a promise, and we pass the promise. Here's our thread here, and it says hello world, and then we get the future. Anyway, this is how it all works. You call producer and consumer, you call join, and it's going to print hello world. Hello world. Set from a different thread. I'm not going to talk about that one or that one. Oh, okay, this is C++ 17. We should talk about this because it's topical. Okay. So what I have here, I have a bunch of ways of calculating a dot product or a inner product, as they call it in the algorithm library. So we have many ways of doing it. I have a for loop, do-it-yourself dot product, a for loop with iterations, range space for, FMA, fuse, multiply, accumulate, that does A times B plus C in minimal clock cycles. It's supposed to be really fast, we'll see. And with the loop iterators with an FMA thing, C++ 11 inner product, 17 transform sequential, transform parallel, and just in case it's using a thread pool, let's call it a second time to see if the time goes down. If it's using a thread pool and it started the threads up when we execute it a second time, it'll be faster. Well, actually here I got the results right there. So rather than run it, well, actually, why don't I just run it? And we'll look at the results. Okay, there's some results, and here's a table. So again, depending which compiler you use, determine the efficiency of the runtime library and how the same code, just compiled different ways, and some of the times, well, they're not bad. 908 microseconds, well, okay, millisecond, big deal. This is interesting here. Notice that often CLang is the faster compiler, but not always. So the C++11 inner product, it happened to be quicker in the G++ compiler. But most of the other time, CLang was quicker or the same speed. I think I got tables at the bottom of this one. Yeah, so this uses accumulate. So accumulate, dot product takes two series and multiplies it pairwise together and adds it up. Accumulate just adds it up. So here's all sorts of different ways of adding them up. And G++ 9.2 and Clang 8. And you can see the times and who wins. They're either pretty close or Clang just edges a bit ahead. So, like here, Clang win there with sequential execution, and for parallel execution, it's pretty close. Now, what I want to mention about the inner product example here, who's heard of AI? Okay. Who's coded any of it? Nobody, okay. No, okay, I'm joking. Okay, so most of it is a dot product, right? You calculate the weights times the variables and stuff. So you're calculating dot product. So this dot product example is AI, meaning 25 words or less. This is how you can make your AI stuff go fast. So I would say if you want to make your AI stuff go fast, C++ 17 transform reduce parallel. And it's going to make your AI go fast. That's just the one program. I thought I had 40, I only had 30. Oh, thread local storage. This is kind of an interesting add-on. The thread local storage is, what it means is every thread has a private copy of whatever you allocate in thread local storage. So here we go. With thread local storage, I declare an integer, and I call it thread local int, and I set it equal to 42. So here I have a thread, and I say, I printed out the variable coming in, and then I set it to 3 and print it out. And then I bump this. Now this is in main, right? So which thread local storage is it going to bump? It's going to bump the value that's allocated to main. Similarly here, I have another thread B, do the same thing. There's 3, 4, 5, 6. Each time I bump thread local storage and print it out. So, whenever it comes into the thread, it happens to be a copy of what the compiler set up when it compiled the program, which was set at equal to 42. And then you set it to whatever. So the first thread set it to 3, the second thread set it to 4, et cetera, et cetera. And then in between calling each thread, main bumped its value. So it bumped it, whatever it was, 4 times. So 42 plus 4 is 46. Thread local storage. I've never used it, but I might someday. Anyway, okay. So that's it for my short fragment programs. And now what I wanted to do was talk a little bit about pipelines. And I'm not going to bother, this was written for a Raspberry Pi. And it ran about 7 to 10 frames a second. On this higher speed laptop, I can run the pipeline. So there's 4 processes in the pipeline. It grabs the frame, that's one thread, and then it feeds the data into the second thread, which smooths it. The second one, the third one does the edge detection, canny edge detection, and the fourth one does the compositing and the display. So again, on the Raspberry Pi, we were limited by the frame acquisition rate from the Raspberry Pi camera, and we were able to get it up to 30 frames a second by doing this from this, 7 frames a second. All on a Raspberry Pi 2, which was the first 4-core model. I'm not going to bother running it. I have it here with me if anyone wants to see. But anyway, so that's kind of cool. Oh, I got to kill it the other way. Okay, here's the times for the processing. So on a 100 frame sample, that's the time taken for all 100 frames. So that's the time per frame. So the grab it, 35.76 milliseconds. Again, this was on a Raspberry Pi 2, so it'd be faster on a 3. And if you take a look here, our longest computational time was our canny. But it happens to be less than this. So that's the frame rate is going to determine our maximum speed. Now, if all these things can be done in under 35 milliseconds per frame, we're good. We'll run at 35 seconds per frame. And this was on the Pi 2, and on the Pi 3 it ran at 30 frames a second. Anyway, so you get the idea here. So the first thing you want to do whenever you're threading anything is look at your computational budget. See where it makes sense. Can you speed it up? You need to know those numbers. If your edge detection takes longer than your frame time, guess what? That's going to determine your frame rate. And if it's going to be less than that, then your camera acquisition's your frame rate. So again, this used barriers and a pipeline. Everybody waited at the top, grabbed the frame, feeds it down the pipeline. This guy did this. Anyway, so they all go up the top and wait. And the last guy's there, boom, they all fire. Last guy's there, boom, they all fire and do their thing. So this was a barrier with condition variables. Okay. So this took 2 seconds to calculate a Mandelbrot curve. This is just an example. Okay, there's our Mandelbrot curve. This is an example of an embarrassingly parallel problem. Each pixel, it loops through until it either diverges, and you count the number of iterations that it goes through before it diverges. If it diverges, you color it black. It's just an example of something more computationally intensive that is a little different. Now, so if you thread the for loop, and when we did this, I was using 4-core processors. This runs on the Raspberry Pi, by the way. Then if you see the first thread would do the top quarter of the screen. The next thread would do between the half and the top quarter, and the third thread did from the middle down to the third quarter, and then the last thread did the bottom. So if you take a look, where's the black? The black's in the middle. So if you count the threads 1, 2, 3, 4, thread 2 and 3 are going to do all the work. So guess what? On a 4-core processor, it ran in twice the time, or twice as fast, as expected, because essentially you're just using 2 cores. 2 of the cores don't do any work. So the solution to that is a thread pool. You assign a scan line to a thread in the thread pool. So the thread pool threads that take a lot of time, they're going to take a lot of time. But the thread pool items, like the first one and the last scan line, whatever, are going to finish very, very quickly. And then they're available to go and maybe do some hard work. So I just want to show you the results of using a thread pool. So this is using a thread pool, and I can scroll around, and I got to be quick because, anyway, I'm not quick enough. So that's a lot better than whatever it was, 3 seconds per frame, just using a thread pool. Oh, I lost it. Anyway, home. So threading is massive. You can get some really impressive performance gains out of threading. Thread pools, everything we talked about tonight. Barriers for the pipeline to make the image processing pipeline go at the frame rate of the camera here. Thread pools to balance or load. You can view it as load balancing between the threads. Oh, one other thing I wanted to show, and that was a Raspberry Pi project. Client came to me with a shoebox of Raspberry Pis and said he wanted to build a video player for helicopter training films. And let's see, where is it? And so my question was, he gave me Raspberry Pi 3, and I was in a day and a bit, I got his application running. And then I wanted to know, could you use a Raspberry Pi 0? This is a Raspberry Pi 0. The nice thing about them, they don't need a fan. They're power miser. You can use a small power supply, cell phone charger. You don't need a 2.5 amp charger like you do for the Pi 3s, and the Pi 4s are even worse. You need a 4 or 5 amp charger. Anyway, so it's just, that's it. There's nothing to it. So what he was doing helicopter training films, and they fly helicopters offshore to the oil derricks and stuff like that, and he spends a lot of time and effort getting fairly high quality animation to make these things go. And historically, he distributed on a DVD, and people would steal it. The next thing you know, on another oil platform, there's his training video. And what he wanted to do was encrypt it. So what we did is we took the serial number of the Pi, which is in the file system, and used that serial number to encrypt the data. So we made a program that would copy the data onto the SD card in the Pi, and another program, the player, would decrypt it in real time and spool it out to the HDMI port. So we had to answer a few questions. Was there enough horsepower? I knew that the Raspberry 3 did it like a piece of cake. And I needed to know how to do it on the Pi Zero, or could we do it on a Pi Zero? Maybe there's not the computational resources available, and it turns out there was. And so the simple thing is just to run your program and print these times out. So how much time was used? Okay, this was that's how long the player played for, 9 minutes. No video, oh, okay, sorry. And this isn't coming up. Okay. So when it played for 900 seconds, 854 seconds, you can see the time that each portion of the playback thing. So user system, that's what we use as main. And I spawned the player. This is what the player used, the child. So 150 seconds out of the 900 were used by the player, and diddly squat was used by us. So the decrypting actually was not a computational load on the system. It just went. And the player was the computation, what took most of the CPU cycles. Now, I had to know, if I'm going to guarantee to the client that this is going to work, I had to know these numbers. And I had to know that things weren't going to block. I had to know that the buffer pools weren't going to starve or be flooded. And then by the time it got scheduled again, something else starved. And anyway, so I had to know all that stuff. So the big thing I had to do was instrument my program and figure out in gory details how to make it go. So we read a FIFO, or we created a FIFO. So the decryption pass wrote to the FIFO. Now, if you write to a FIFO, it can block. So we wrote half the FIFO size. And then the player would read from the FIFO, and as soon as it read half of the FIFO, then my process would wake up again and would put another half back in there. So everything went tickety-boo with maximal transfer size, and we set the maximal FIFO size to that supported by Unix. You can make system calls and inquire what FIFO sizes are and your max, and you can set it and blah, 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 blah. So we set that to the max, and then everything was tickety-boo, and it ran. So it was running earlier. Any suggestions, Brad? Is it working? Oh, okay, we're live, okay. I won't touch it. So one of the complaints from the client was it took too long to boot. We agreed. It does take a long time to boot.
Welcome on board your Canadian Helicopters offshore flight. Please pay close attention as we review the safety equipment, features, and procedures of the Sikorsky S-92. The S-92 is a twin-engine helicopter that is equipped with state-of-the-art avionics.
Okay, Brad's an expert on Bluetooth. I'm not. He's got a robot that he controls with Bluetooth with his phone. So I said, oh, you're the guy to do this for me. Figure out how to make that thing pause from your phone. So he did. Anyway, big hand for Brad. So again, this was a lot of fun. It was interesting. I know all sorts of things about helicopters that I never knew before. Did you know you can't wear a baseball cap on a helicopter? They're afraid it might get sucked into the jet engine. You can't take a camera or a laptop or a tablet. For the same reason, your camera might get sucked into the jet engine. You can put it in your bag and carry your bag because your bag's heavy, right? So it's not going to get sucked into the engine. That's what they figure. So all your gadgets have to go in your bag. You can't do this. You can't do that. And if you watch the whole 9-minute training video, which we won't unless you want to, you'll find out about immersion suits. The immersion suits are really cool. They have a little scuba tank that's good for 5 minutes. So when the helicopter turns upside down in the water, and it's at night and it's dark, they have lights, all sorts of stuff, lights on your suit, and you got anyway. When the helicopter pilot says dive, 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 or whatever he says just before you smuck the water, then you put the breather tube in and away you go. I mean, I thought it was really cool. And this was all because all this extreme safety stuff was all because of the ocean, not the Ocean Ranger, the Cougar helicopter crash where 18 people died. So that was bad politics, so they made them get really tight and do really thorough safety stuff. And it's absolutely amazing, the level of safety that they're going through. So I learned a lot about helicopters. And would I fly in one? Before I would have. I'm not so sure now. But so any questions about threading? So go make lots of money with threading. It's really cool. But tell everybody it's hard. That you're the guy. Only you know how to make it go, and you'll do well. So, thank you.
To thank Greg, we're going to give our now traditional Purdy's chocolates. Let's give Greg one more round of applause. Okay, so our next event, I posted it today. Hopefully some of you saw it. It's going to be October 29th. Kate Gregory is going to reprise her CPPCon 2018 keynote, Simplicity, Not Just for Beginners. And this is a full 90-minute version. I saw it at CPPCon, not to be missed. I hope to see you all there. Definitely, we are interested in anybody who would like to speak at a future event, a future meetup of this user group. If you have ideas, if you want to talk, please get in touch with me. If you think you might want to talk and you don't know how to put together a good talk, absolutely I can help. Absolutely go to the Include C++ Discord. There's a whole channel on speaking. Everybody will help you put together good talks. We're also looking for sponsors, always looking for sponsors. It's possibly the last time. Circling back, our next meetup is not going to be here. Our next meetup is going to be at Oanda, hosted by Oanda, and that's pretty exciting. We are possibly going to be able to come back here, but we do not know, so we are absolutely looking for spaces. That is a great way to sponsor the group if you know of an appropriate space to have meetups. We also like money. We love any kind of support you can offer. Okay, so what am I going to say now? You don't remember. Raise your hand if you are trying to hire people for C++ jobs. 3 of us. Raise your hand if you are looking to be hired in a C++ job. Several of you. Okay, there's cookies in the back. Let's talk. Thanks for coming.